Okay, so let's look at one where I'm going to have you kind of work on it on your own. So this is still graphing. Rational functions. So let me word this the way that I probably would for a test. Okay, so I want you to graph this by finding all intercepts all asymptotes, and additional points if necessary. Okay. Spoiler alert, they're going to be necessary. Okay, you're going to have to at least pick a couple. You're not going to possibly have enough points to graph this whole thing. So I want you to see if you can take maybe 2 minutes and see if you can get the important pieces of this. So basically there are 4 things you should be finding. Y-intercept, also what? X-intercept, right? And then what kind of asymptotes are we finding? Both vertical asymptotes, but also what? Horizontal, and then put it all together in a graph and see what you get. Okay?
So do we need to find the symmetry, or is it like...
Yeah, so I'm letting you skip that part on this one. Yeah. Because I already told you that's not super important to me, so. So if you're watching back the video, then pause the video and see if you can work it out. So maybe like 30 more seconds, and then even if you're not quite done, we'll finish the rest together. So let's run through, how do you find the y-intercept again? Set x to 0, right? So you just need to find f of 0. So you do 2 times 0 plus 1 on top, 0 minus 3 on bottom, so you get 1 over negative 3. So how would I write that as a point again? 0 and then negative 1/3. Notice it doesn't matter where you put the negative sign. Okay, so I'm going to circle that. What about x-intercept? You set y equal to 0. More specifically, you set the what equal to 0? Numerator. So you're going to say 2x plus 1 equals 0. So you're going to get x equals negative 1/2. But how I'm going to want you to write it is negative 1/2, comma 0. Okay. What about vertical and horizontal asymptotes? Vertical, you simplify what you can't, right? And then you set the denominator equal to 0, right? So you set x minus 3 equal to 0. So you get x equals 3. And then what about horizontal asymptotes? You notice that the powers are what? Powers are the same. So the horizontal asymptote is y equals 2 over 1 or just y equals 2. So if you could get all those building blocks, then you're well on your way to getting a decent graph, right? Negative 1/3 would maybe be about here. Negative 1/2 maybe about there. Vertical asymptote at 3. Horizontal asymptote at 2. So it looks like the left side we're pretty golden on, right? We already kind of know what it looks like, so we'll just sketch it, right? Make sure that it gets really close to the edge without actually crossing it. But what are we still pretty unsure about? This time the right side, correct? Okay, so which additional points did y'all end up picking? You can pick anything you want as long as it's to which direction. Which direction should you probably be going with the points you choose? Something over here to right to the right. So I would probably choose 4 and 5 because they are literally the first two things I see to the right. And then how do you get the answers? Plug them in. Okay. So you should have gotten 9 here and you should have gotten 5.5 here. 5.5. So let's graph that. So I'm going to do this one first because I just think it'll be a little easier. So that'll end up about right here, right? I think I already went up to 5, so 6, 7, 8, 9 won't be too difficult. And so 4 would be about here-ish. And so it should do something kind of like this. Okay, so if you could do that without, having to look back at your notes for every single little thing, then you pretty much know what I would expect you to know for test 2. Okay, as far as the graphing stuff goes. Okay, so let's look at, we're not really going to focus on graphing this so much, but there actually is a third type of asymptote. And again, I'm not going to worry you with looking at what the graphs are. But if vertical asymptotes are vertical boundary lines, and horizontal asymptotes are horizontal boundary lines, what do you guess slant asymptotes are? They're just slanted boundary lines, right? So it's basically a diagonal boundary line. That the graph approaches but doesn't touch or cross. So it's still an asymptote, meaning that it's going to get close, but not all the way. Okay, so again, I'm not going to focus on you graphing the slant asymptotes so much, but I do want you to be able to find them. But just so we know, not all functions even have them. Like none of the ones we've looked at so far even had a slant asymptote. None of the ones we've graphed so far. So notice there was no like diagonal boundary line that the graph was getting close to, right, in any of the ones that we graphed. Okay, so here are the very small group of functions that will have it. Only functions in which the numerator's degree is exactly 1 more than the denominator's degree will even have one of these? And so the vast majority of rational functions aren't even going to have this at all. Okay, but there are a select few, and so that's why we're going to talk about it briefly. So I'm going to tell you how to find them in a minute, but I want to show you what I mean by the top degree is exactly one more than the bottom. So notice in this function, what's the power of the top? Or degree? 2, right? What's the degree of the bottom? 1. Notice that it's one more, okay? Also, something like this would have 1. X cubed minus 2x plus 3 over x squared plus 4. Anything where the power on top's 1 more than the power on bottom, okay? So I'm just going to say both of these have slant asymptotes. All right, so now that we covered kind of which ones will even have one to begin with, let's talk about how to find the ones that have it. You will find the slant asymptote by actually dividing the numerator by the denominator. We have 2 ways to do that. So what were our 2 ways of dividing polynomials? Long division and synthetic, yes. Okay, which one do we probably like better? Synthetic is what we like better, but remember, synthetic doesn't work for everything. It only works when we're dividing by something very simple. So there possibly might be some problems we're going to have to pull out long division too. Okay, so you divide and you ignore the remainder. And the answer that you get is the equation for the slant asymptote. So unlike what we did before we were actually very concerned with what the remainder is. For slant asymptotes, we're not going to be all that concerned about it. So just know that vertical and horizontal asymptotes are more common, okay, but it doesn't mean we don't need to know how to find the slant asymptotes also. So I want you to be able to, for test 2, find all the asymptotes, even the slants if it has one. I'm going to sketch for you what they look like just so you can visualize it, but I'm not going to expect you to graph it on test 2. All right, so let's say that I gave you the same problem that I did above. That first example where I said, yes, this would have one. So when I say find all the asymptotes, I actually need you to run through how many different types of asymptotes do we have now? 3, okay. So the first 2 are pretty easy, right? For vertical asymptotes, I just need to set the denominator equal to 0. Sorry, x minus 3 equal to 0 is what I meant to write there. By the way, you can simplify this if you'd like, but notice that it doesn't factor into anything that would simplify. So I mean, it's worth writing down, right? We got x plus 3, x minus 2, but nothing cancels out. So we just set x minus 3 equal to 0, and we get x equals 3. Okay, for the horizontal asymptote, remember this is the 3 cases thing. Okay, so what do you notice about the power on top for this function? Power on top is bigger. Do you remember what conclusion that is? It's been a minute. Means none? Yeah. If power on top is anything bigger, we don't have a horizontal asymptote. The slant asymptote, we already know it has one, right? Why does it have one? Because the power on top is what compared to the power on bottom? Exactly one bigger. Okay. So remember, so we're going to say it has one since power on top is one bigger. So remember, to find it, you just divide. Okay. So can we use synthetic division, or are we going to have to pull out long division for this one? We can use synthetic, right? So remember, we are going to divide by 3, right? We change the sign of this one, and then we line up the coefficients for what we're dividing into. We bring down the first number, right? And then we multiply, add, multiply, add. So I don't want to go over this too much because I feel like we've already done this, okay? But this is the remainder, and what did we say we were going to do with this, with this slant asymptote stuff? We're going to ignore it. So all we care about is really what we get here, okay? And what do we get there? 1x plus 4, or just x plus 4, okay? So that means the slant asymptote is actually just y equals x plus 4. So it's whatever you get when you synthetically divide or divide in general, ignore the remainder. Okay. So just to kind of let you know what this looks like, okay, I'm going to sketch it with you just because I want you to be able to visualize it if you're a more visual learner. But other than that, just know that I'm not going to make you graph it. So we know there's a vertical asymptote at 3, right? Remember how I said there was no horizontal asymptote at all? So hopefully you remember, but we know how to graph x plus 4. We should, right? What's the slope of this line? The slope of x plus 4 would be what? What's the understood number in front of x if I don't give you one? 1, right? So the understood slope is 1. So basically it crosses at 4, and then we go up 1 over 1. So essentially this is what the diagonal asymptote looks like. And then this vertical asymptote kind of carries on here too. And just so you know, this is how the graph looks. It stays bound in these lines right here. So I'm not expecting perfection here, but it does something kind of like this. So it just squeezes inside the two lines. So once you've drawn the lines with the slant asymptote, you just draw the curves up inside there. But again, I'm not going to really make you graph this. I just wanted you to be able to visualize what it meant. Okay, so I want to look at one more with a slant asymptote, but I don't think we really have time to finish it for today, so we'll just look at that next time. So make sure you bring your notes from today. Camera angle's a little different. All right, so this is going to be continuation on 3.5 again. So I'm just going to say continue 3.5 again, okay, because we did it kind of in 2 sessions last time too. We ended last class talking about slant asymptotes. So I want to make sure that we know how to do that in different situations. So when I say find all asymptotes, that means I want you to tell me the vertical, the horizontal, and the slant ones. Okay, remember slant asymptotes don't exist with every type of equation. So let's say that I gave you this equation. X cubed plus 1 over x squared. Okay. So let's just kind of run through our list, right? So I'm going to remind you of how we do these. How do we find the vertical asymptotes? Remember, you simplify first, which notice there's nothing to factor / simplify, and then you set what equal to 0? Well, not x. You said the denominator equal to 0. I think what you're thinking about is already what the answer is going to be, which is fine. Okay. So if you set the denominator equal to 0, notice we'd get x squared equals 0, which is just x equals 0. Okay, so there's a vertical asymptote at 0. Remember that I want you to write those as x equals. Okay, and for the horizontal asymptotes, remember they look like y equals. For the horizontal asymptotes, we have 3 cases. Okay, remember we compare the powers on top and bottom. That's the 3 cases. So I'm just trying to jog your memory for what we did last time. But note that the power on top is bigger. And if the power on top is bigger, what's the conclusion? No horizontal asymptote, that's right. Okay, if it's anything bigger, the power, then there's none. What if it's smaller? What was it, just to remind ourselves?
0.
If it's smaller, it's 0, y equals 0, and then what if they're the same? What do you do?
The leading coefficient.
Yeah, like pull the top number over the bottom number, and that's it, right? So a slant asymptote, first let's talk about if this has one and why. Okay, so remember, note, or pay attention to the fact that the power on top is 1 bigger than the power on bottom. So that's the key. So because it's exactly 1 bigger, what does it mean? There is one. Okay. Notice there'll never be both a horizontal asymptote and a slant asymptote at the same time, because if the power on top's anything bigger, there's no horizontal asymptote. Okay. So remember, what we're supposed to do is divide and ignore the remainder. And whatever we get for an answer, that's the equation for the slant asymptote. Okay. So this is how we always find the slant asymptote. So let's come back up here, right? Notice we cannot use synthetic division here. How come? Remember, synthetic division is only when the bottom is something like what? It has to be like x plus 1 or x minus 5. It has to be x plus or minus a number, okay? So note that we have to use long division here. But luckily for us, that's not that difficult. Okay, we have to use long division because we're dividing by something more complicated. So here is a quick reminder of long division. Okay, remember, for long division, you only look at the first terms anyway. So we only are going to pay attention to these two, right? And we're going to ask ourselves, what would happen if I divided an x squared out of an x cubed? What would I have left? An x, right? So I'm going to kind of wedge that in between these two. It really shouldn't go above either one of them. Okay, do you remember what I do with this x then? Yeah, you multiply down, right? So x times x squared is, of course, x cubed, right? And then we subtract, right? So what happens to the first term? That goes away, right? And what do we do with the next term? Bring it down. So notice, like, I can't do this anymore, right? Like, I'm done, because I can't divide an x squared out of a 1, right? Which means this is my remainder, right? And what am I supposed to do with the remainder in this? I'm supposed to ignore it anyway. Okay, so the slant asymptote is just what we got up here. So the slant asymptote is just y equals x. So it's the equation with a slope of 1. That's it. Okay. So we were kind of rushed at the end of class last time, but remember I said I'm not going to make you graph these. I'm just going to make you find them. Okay, so what I will make you graph is vertical and horizontal asymptotes, but slant asymptotes, we probably won't mess with that. Okay. Okay, so the last thing from this section, and then we are going to move on to something else. So I want to look at 2 common rational function graphs. Remember, the word rational just means fraction. And then I'm going to ask you to remember something from test 1 that we're going to make some applications for this new rational function graph. So here are the two kind of basic looks for most of the rational function graphs you'll have. So let's look at what the difference between 1 over x, the graph is, and then what 1 over x squared looks like. So here's the graph of 1 over x. It is probably the more common of the two. It's got a curve on the right and it's got a curve on the left. But the most basic one is 1 over x. Okay, we're going to talk about how we might be able to change that in a minute. Okay, so the same type of graph when it's 1 over x squared just looks like this still, but this left piece is actually a mirror image of it. Okay. By the way, you might be able to figure out why that is, right? What kind of numbers am I always going to get when I square numbers, no matter if they're negative to start off with or positive? Like a negative number squared is going to be what? Positive, so that's why these two stay up above the x-axis, whereas this one, this part's negative and this part's positive. Okay, so you don't have to really know that. But what you do need to be able to do is you can actually, from Unit 1, you can apply all 6 transformations to these. Okay, and if you've forgotten that, you might be able to refresh your memory in section 2.5. In other words, these are the simplest / parent functions, and so we can make some changes, and then we should be able to describe what that's going to do to our graph. So probably on test 2, I would be more likely to ask you to describe for me what's happening than I would be for you to actually sketch it. So let's do an example where I ask you to do that with kind of a variety of different ones. So I want you to describe the graphs compared to the graph of f of x equals 1x that we showed above. So you won't really even need to skip too much space between these, but let's write all of these out first. And this is not all of them, but it's a good start. So when I say describe, I don't really expect you to sketch it. I just expect you to kind of explain to me what's different. Okay. So before we go on, just know that all of the above graphs will have the same general shape as 1 over x. So maybe we don't have to explain that every time. So it'll be that 2-part curve kind of thing. So my question really is, like, what change needs to occur? Okay. So hopefully you remember section 2.5 and you don't have to go back and review it too much. Okay. So what do you notice about this function? It looks the same, except what did I do at the end of it? I subtracted a 3, right? So do you remember what kind of shifts happen when you add and subtract a number at the end of a function? It's up or down, right? But because it's minus 3, it's going to be what? Down, so it's going to be shifted down 3 units, right? What if it would have been a plus 3? Then we would have said what? Up 3. Okay. All right, so let's talk about this one. Okay, what do you notice about the plus 2? It's not at the end this time. Where is it? It's inside, right? So what kind of shifting was inside a function? Left and right, correct? So remember, this is the oddball one, right? So which way does it actually shift? Left. Okay, so if it would have been a minus 2, it would have been to the right. Remember, horizontal shifts are opposite of the direction you might think. All right, so what about this one? We have two shifts happening, right? We have a shift of what according to this?
Right, three,
Right, 3, and then what is this going to do to the graph? Up 4, okay. So this would be shift right 3 and up 4 units. Remember, you work from the inside out, so technically you would do the right shift first, right? Because that's the one on the inside. And then